Hello everyone. Let's begin with a simple thought. Why is it that chloroform behaves so differently from chlorobenzene, even though both contain chlorine? And LT, break time is equal to 0.5 SN/GT. The answer lies in the chemical reactions they undergo. Haloalkanes, with their polar carbon-halogen bonds, are quite reactive and undergo nucleophilic substitution, elimination, and even metal reactions. And LT, break time is equal to 0.5 SN/GT, but haloarenes, with halogens attached directly to an aromatic ring, are surprisingly less reactive. This is due to resonance and the special character of the carbon-halogen bond in aromatic systems. Today, we'll journey through the fascinating chemistry that separates haloalkanes from haloarenes.
Let's begin with nucleophilic substitution. The nucleophile replaces the halogen atom. The general reaction is Rx plus nu minus gives R nu plus X minus. Here, Rx is the haloalkane, nu minus is the nucleophile, and X minus is the leaving halide ion. So the halogen is displaced, and the nucleophile takes its place on the carbon. Now, this can happen in two ways. In the SN2 mechanism, the nucleophile attacks from the opposite side in a single step, leading to inversion of configuration. In contrast, the SN1 mechanism is a two-step process, where the halogen leaves first, forming a carbocation intermediate, followed by nucleophilic attack. That gives a racemic mixture if the carbon is chiral. Reactivity depends on the substrate. SN2 is fastest in methyl halides, while SN1 is most favored in tertiary halides because of carbocation stability. This delicate balance explains why the same halogen can behave so differently depending on the carbon skeleton it is attached to. Let's now discuss ambident nucleophiles. Nucleophiles that have more than one possible site of attack. Take the cyanide ion. It is written as -C triple bond N. This ion can attack either through the carbon atom, which gives a cyanide product, or through the nitrogen atom, which gives an isocyanide product, for example, with potassium cyanide. R-X plus KCN gives R-C triple bond N plus KX. Here, the carbon atom of the cyanide does the attacking, so the product formed is an alkyl cyanide, also called a nitrile, but with silver cyanide. R-X plus AgCN gives R-N triple bond C plus AgX. In this case, the nitrogen atom of the cyanide is the attacking site, so the product formed is an alkyl isocyanide. Similarly, consider the nitrite ion, written as NO2-. It can attack either through the oxygen atom or through the nitrogen atom. This leads to two possible products. When the attack is through oxygen, the product is an alkyl nitrite, written as R-O-N equals O. When the attack is through nitrogen, the product is a nitroalkane, written as R-NO₂. So, ambident nucleophiles are special because the same nucleophile can give two different products depending on which atom makes the attack. Now let's turn to elimination. When a haloalkane reacts with a strong base, instead of substitution, it can lose a hydrogen atom and a halogen atom to form an alkene. This is called β-elimination, since the hydrogen removed is from the beta carbon. For example, when 2-bromopropane is treated with alcoholic potassium hydroxide, we get propene and hydrogen bromide, written as CH3CHBr CH3 plus alk KOH gives CH2 double bond CH3 plus HBr. According to Zaitsev's rule, the more substituted alkene, that is, the one with greater alkyl substitution around the double bond, is the major product. This competition between substitution and elimination depends on base strength, temperature, and the structure of the haloalkane. Haloalkanes also react with metals to form important organometallic compounds. With magnesium in dry ether, they form Grignard reagents, RMGX, which are highly reactive and versatile in synthesis. With sodium in dry ether, two molecules of a haloalkane combine to form a hydrocarbon in the famous Wurtz reaction. For example, two molecules of bromothane with sodium give butane plus sodium bromide, written as 2CH3CH2Br plus 2 Ne gives C4H10 plus 2 NeBr. In the Wurtz-Fittig reaction, an aryl halide reacts with an alkyl halide in the presence of sodium to form an alkyl substituted aromatic compound. These reactions showcase how halogen atoms can act as gateways to building larger and more complex carbon skeletons. Now let's shift our attention to haloarenes. Unlike haloalkanes, haloarenes resist nucleophilic substitution. Why? Because of resonance, the carbon-halogen bond acquires partial double bond character. Also, the carbon attached to the halogen is sp2 hybridized, making it shorter and stronger. On top of that, the instability of a phenyl carbocation discourages substitution. But haloarenes do undergo substitution under special conditions. For example, chlorobenzene can be converted to phenol when heated with aqueous sodium hydroxide at 623 Kelvin and 300 atmospheres pressure. On the other hand, electrophilic substitution is more common. Chlorobenzene reacts with chlorine in the presence of Fe-cell3 to give ortho and para-dichlorobenzene. Interestingly, the halogen already present directs incoming groups to ortho and para positions, even though it slightly deactivates the ring. So let's wrap up. Haloalkanes are versatile compounds that undergo nucleophilic substitution through SN1 and SN2 mechanisms, elimination to give alkenes, and reactions with metals to form organometallics. Ambident nucleophiles can produce linkage isomers such as cyanides and isocyanides, or nitrites and nitroalkanes. See? Haloarenes, in contrast, are far less reactive in nucleophilic substitution due to resonance and bond character. However, they readily undergo electrophilic substitution, with halogen atoms acting as ortho-para-directing groups. So, the chemistry of halogenated compounds is rich and varied, with reactivity dictated by structure, hybridization, and resonance. I hope this session helped you connect the dots between theory and the fascinating reactivity you'll soon practice in the lab. See you in the next class for more exciting chemistry adventures.